Welcome to Nano Matters, the podcast that explores examples of nanotechnology. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Here with me today is Xia Hong, Associate Professor in the Department of Physics and Astronomy at the University of Nebraska-Lincoln. So Xia, I understand that you're exploring novel materials for advanced electronics. Can you talk a little bit about your research?
Sure. First, thanks for having me. So we work on nanomaterials that can be really make an impact in non-volatile memory. So I can tell you a story about how I got started in the field. When I was in graduate school, that is, I think, the early days, people realized that the semiconductor industry cannot sustain its scaling. So we work on computers, cell phones. We want to pack more and more chips, more information on the device. One of the problems is really the current technology is based on semiconductor. And if you keep making the device smaller and smaller, the energy consumption is not sustainable. But back in the time when I was in graduate school, the industry people actually don't believe us. They said the Moore's law will never die. And we come up with different material strategies. We switch to different crazy nanomaterials. And they just don't believe that it will never happen. And a couple of years ago, I met someone who was my graduate school classmate, and she told me, she's currently in industry, she told me they believe it now. It's happening. They have to switch. And so you can see that fundamental research sometimes lead the industry for decades. And when you're doing fundamental research, you are really making impact for what is along the line, maybe 10 years or 20 years later. That's basically what we're doing. One of the research interests we're interested in is how to lower the power density. So I will use magnetic memory as an example. So you have the information coded in magnetic spin directions. So to switch that spin directions, currently they basically have a current that generates a magnetic field to switch. And this current is basically consume lots of power. And we want to take an alternative approach, which is use voltage instead of current so that the power can be lowered. So what we're trying to do is basically create a bilayer material. One layer is magnetic oxide. On top of it is what's called a ferroelectric oxide. This ferroelectric oxide has the dipole moments that are aligned, and you can switch the dipole moment using the voltage. So to couple these two materials at the interface, it is possible actually change the magnetic moment in the bottom layer by switching the dipole moment at the top layer using a voltage. So basically, this is a voltage-controlled low-power non-volatile memory that we're trying to develop.
So you talked about these different layers of oxide materials, and I understand that you grow these crystals on top of each other. Could you talk a little bit about the techniques that you use to grow these crystals and then some of the tools and instruments that you use to study them?
So we do physical vapor deposition. So the specific technique I use is sputtering. It's more like you start with a template, and you somehow kick out some atoms from a source called target, and the atoms would land on the template and find its own way. So if the environment, such as the gas environment, the temperature is suitable, the self-organize into a thin film. And what we want is grow actually one atomic layer at a time. And the oxide materials we work with, known as perovskites or spinels, they have very geometrically very simple structure. You can have very diverse properties because you choose different elements, but they actually crystallize in a pseudo-cubic structure. So that means we can just grow a couple of atomic layers of a magnetic oxide, and then starting the growth again with a couple of nanometer of ferroelectric oxide. And at the interface, they're actually registered with the atomic precision. And it's because of this very strongly coupled interface, we can actually control magnetic property using electrical means.
I think that's a great description of the growth of these very thin films. How do you study them? How do you make sure that you have this registry at the interface that you talked about?
Yeah, so we take pictures. One way to think about it is when we take a photo picture, the tool you use is light. But if you want to see an atom, you really need a different tool, a different probe, which is the electron. So we do what's known as a transmission electron microscopy. And because of the electron wavelength is on the order of the atomic spacing, so you actually can take a picture, really see how the atoms are arranged. And ideally, you would see that I have one atom of ferroelectric oxide on top, sitting exactly on top of the magnetic oxide. And that's the kind of material quality and the level of control we can have.
One of our podcast guests has encouraged us always to ask the question, if you were to give advice to a high school student that would be interested perhaps in pursuing advanced nanoelectronics and maybe working in research or eventually in industry, what advice would you give that student?
I think one advice I would give is don't forget why you are interested in science. For example, I was really interested in physics in high school because I like solving problems. But when I got into the lab, I didn't realize that everyday activity I have to deal with is wrenches, pumps. I need to tighten many screws, pump down the system, and it leaks. So there are lots of non-scientific activities. And you work on a project, you will fail many times. And it's not so straightforward because you're creating something that does not exist in nature. It's a new platform. Very little is known. And there's no solution anywhere. There's not a solution manual with a standard answer that you can look at. So this is very exciting, but it's also very hard. So if you always remember what got you into this field, in the very beginning, you want to understand how nature works. You want to create something new. And that's what keeps you going, right? That's what motivates you to turn 100 screws and leak check. So there's a balance. There's some routine, hard lab activities. There are many frustrations you have to face, but you have to trust nature is beautiful and you will get there.
I think that is fabulous advice. And I certainly remember days where the vacuum system wouldn't seal, and I can completely relate to what you're saying. So I want to thank you again for taking the time to talk with us today and just ask, do you have any closing thoughts that you'd like to share with our listeners?
Sure. It's related to what we just discussed. So I have lots of actually undergrad students working in my lab. And every summer, we actually host summer high school interns. It's very interesting working with students with different backgrounds and different levels. And they form wonderful teams. I think if you're interested in science, you should get hands-on activities, get exposure early. And there are many research labs like my lab are willing to give this opportunity to those young talents. So nanomaterials, nanotechnology is basically an emerging field with lots of opportunities. I think it's a wonderful field to make your careers in. So if you're one of the young talents interested in science, please join us to make an impact to the society.